Hello friends, this is Durga again from IT Varsity. As part of how actually data is stored in Oracle database in the form of blocks, extents, files, etc., we have seen details about table, how the data is stored for a table. So we only talk about the representation on the files. We didn't talk about how it will be saved on the files as part of the last video. We will be covering that later, but now we will see how index will be represented in a Oracle database on files. The main difference between index and a table is that index data needs to be sorted on a particular column or a combination of columns on which index is defined, whereas in table data need not be sorted. Data can be stored into the storage allocated for the table, and it can be randomly stored anywhere in the storage allocated. Now when it comes to index, data needs to be sorted on the columns on which index is created. So first let us go ahead and create the index. We will use a deck of cards only in this case, and we will create an index on a table deck of cards on a column called pip in a moment, and then we will see how it works physically, how it is represented on the files which are used by Oracle database. Okay, I'm creating index. Create index deck of cards underscore idx on deck of cards pip. Okay, and click on this arrow button. It will take just few seconds to create the index. It is done, and now let us see what is there in a view called DBA underscore indexes, DBA underscore segments, DBA. So we don't need to worry about table spaces data files, because even the indexes will be created in the default table space itself if we do not specify the table space name while creating the index. And we already covered about table spaces and data files as part of the last video where we spoke about tables. So we don't need to worry about table spaces and data files. We need to check DBA underscore indexes, and then segments and extents related to that index. So DBA underscore indexes, we can leave table name here, but here the segment name is deck of cards underscore idx, which is nothing but the index name. And same is the case with DBA underscore extents. So already we have 70 megabytes of data. So the index properties will be means that the extents might be larger than 64 KB to begin with. Let's see what happens. So you have I ran the query select star from DBA indexes, and it is similar to DBA underscore tables. You can see that initial extent is 65 KB and next extent is 1 MB. And then when it comes to DBA underscore segments, also it shows the same thing, but the size is already 52 megabytes. It's not, we have 3 columns in the table: color, suite, and pip. And pip does not have too much of data. It only have 13 distinct values, which are 2, 3, 4, 5, 6, 7, 8, 9, 10, J, Q, K, and Rs, and they are relatively very small compared to suite and color. But still, the size is almost 80% or 70% of the table data. So, for example, if you run DBA segments query on table, the size of the table is 75 megabytes, whereas the index size is almost 52 megabyte. Why it is so big? We will understand that in a moment. And then you can query DB underscore extents. Okay, so in case of DBA underscore extents, it has 65 extents, and here also the first 16 are of 64 KB, and then rest of them are 1 megabytes. Again, after reaching certain limit, it might start extents of 8 MB also. It's, I think, because of ASSM under the covers, but you don't need to worry much about it. You just need to understand how the data is stored. Now we will try to answer the question why this is 52 MB even though the index is only built on one column called pip, which is actually less than 1/3 of the original table. The reason is, when it comes to index, as I have explained earlier, the major difference between table and index is data is sorted as part of the index. So now if you try to visualize on the data set, it will look like this: select star from deck of cards, order by pip. So data will be stored literally like this. It uses B-tree algorithm behind the scenes. You don't need to worry about B-tree algorithms and try to understand it in detail under the hoods. But data will somewhere look like this. The data will be sorted by pip. You will get all the pips of value 10 because we have 2 to 10 and JQK and us, and the data is alphanumeric. So when you actually sort an alphanumeric, 10 is the first value, then 2, then 3, 4, 5, 6, 7, 8, 9, and then JQK and A, JQK, etc. So you have index like this actually. Let me do pip. Okay, and whenever you try to use a filter condition on the pip, it will try to use the index. But you can run queries like select star from deck of cards where pip equal to 2. It should use index because index is supposed to be faster. And when you run this query, the index does not have all the columns, it has only pip. So it has to go to deck of cards to get the rest of the columns like color and sweet. So it has to have a mapping between each and every row in the index to the each and every row in the table. The difference is, in index, data is sorted by the indexed column, whereas in table, data is random, it is not sorted. So the way these both are connected is by using the RowID. Again, as part of the last video, I have explained what the RowID is. For each and every row, you have the file, you have the extent, you have the block, and within the block you have the relative position of your record. All these things is stored as part of the RowID. So the index does not have the pip itself. When you actually create the index on the table, it also have the pip and RowID, and RowID will be typically very large column, and because of which as index have to store both the pip and RowID, which is very large compared to your color and sweet of the table. The size of the index is pretty large. So the way the index will be represented will be like this. It will be select pip comma RowID from deck of cards order by pip. Okay, and then you can run the query. So this is how the index structure will be represented on the files physically for this index called deck of cards underscore idx. So when you run the query by using where pip equal to 2, as pip is indexed column and the data is sorted, you can actually easily sort the data from sorted records much effective way compared to unsorted data. That's why sorting is very important, and indexes store the data in sorted form, and to have the mapping between the indexed value and the table for the corresponding record, RowID will be the connecting link between the two. Other than that, everything is same. So even index, for each and every index there will be a segment associated with it. It's a one-to-one for a non-partition index, and that segment will be stored as a contiguous blocks in the form of extents, like it is the case with the table. It's the same case with the index. Only difference is indexes will be stored in the sorted fashion using B-tree algorithm. That's the only difference. Other than that, everything else is same. So that being said, let us also talk about partition tables now. We have spoken about tables, we have spoken about indexes. When it comes to partitioning, there are many types of partitioning, but I will use a simple partitioning called list partitioning to partition the data. So let me create the table, create table deck of cards underscore part, color varchar2 30, suite varchar2 30, and pip varchar2 2. So this is the syntax I have copied. Let me partition it on suite. Okay, and let me name it as p1 for partition 1, and the values is we have 4 values for suite. So let spade and then partition p2 values diamond. Okay, now we actually define the table name using list partition, and we can run this query. Name of a partition of a, okay, partition name has to be unique. I just copy pasted it so names remain same, and then run this query. So table is created. Now let me run insert into deck of cards underscore part, select star from deck of cards, and run this query. Okay, now once it is run, we will run this same queries. What is the table name? It's underscore part. So no need to worry about table spaces and data files in this case. So data is still being loaded. Let's wait. And so the table is the data is inserted. Let me commit it, and now let me run these queries. You can see that there is only one entry in the DBA tables, but there is another table called DBA underscore tab underscore partitions. Okay. Because each partition itself is a kind of a table, but instead of creating many tables, we take the route of creating partitions, because you don't need to modify the table names as part of the queries. So partition table is nothing but a union of individual tables under the hood of the same name. So let me run this query. You can see that there are 4 partitions. We have to set table owner here, and you can see that there are 4 partitions with name p1, p2, p3, and p4. This is the high value in each of the partition. And then you can run this db underscore segments, and you can see that for each partition there is a segment. Unlike the table, there is one-to-one mapping between table and segment. If it is a partition table, there will be one-to-one mapping between table and the partition. Sorry, between the partition and the segment. So we have 4 segments, and segment name is still the table name, but you have to include partition name also when you actually try to get the details for a particular partition. Just by using segment name, you will not be able to get the associated segment details for a given partition. Okay, so if you look at this, it will give the size of each of the partition. This one is 25 megabytes, this one is 25 megabytes, this one is 24 megabytes, and this one is 16 megabytes. Okay, and if you count these things, it is almost 90 megabytes, whereas our table, which is not partitioned, it is only 75 megabytes. So why there is a 15 megabyte increase in the size of the partition table? The answer will be in the DBA extents, and you can see that so I'm modifying the query to get the details order by segment name, comma, partition name. And then you can run this query, and you can see that it has 4 segments, this has 3 segments, and this has 2 segments, and this has 3 segments. And you can see that the first segment is around, sorry, the first extent. Okay, let me do the partition name itself. Yeah, partition name and then extent ID also. So if you look at the extent ID, because we are querying the data from existing table, it is determining the extent size on the fly. Okay, and in this case, you can see that there are 896 blocks in this extent, and you can actually look at DBA tab partitions to see what is the initial extent and next extent size. So initial extent is 8 MB and next extent is 1 MB, and these values are reflected at the user level defaults. We can change those things by overriding certain values under by overriding certain values while creating the table. This value, it is taking 8 megabytes because if you remember, when we create the table, it started with 64 KB, and then after a while it went up to 1 megabytes. So at the table space level, it is doing automatic storage management, which is actually determining this initial extent size. So the initial extent size is 8 megabytes, and for that reason, in select star from DB extent, this query, it has very few extents, which is of size close to 8 megabytes for each of them. Okay, this one is almost 7 megabytes, this one is 1 megabyte, this one is 7 megabytes, and rest of them is 8 megabytes. I still completely do not understand why there is a disparity between these things, because at the table space level, the extent size has changed. Let me show that. We are using users table space for everything, right? And here, yeah, you can see that the segment space management is saying auto. So depending upon the usage of your table space, the size, the initial extent and next extent values can change, it seems. But the main thing you need to understand is whether it is a partition table or an index or a table, data will be stored in contiguous blocks which are called as extents, and because of the automatic segment maintenance, the size of the extents will change over time, so that your IO works in effective fashion. And the main difference between a table and index is, in index data will be sorted, whereas in table data will not be sorted, and there will be one-to-one mapping between a non-partition table and between a non-partition table and a segment, as well as non-partition index and a segment. Whereas when it comes to partition table, there will be one segment for each of the table, but the underlying representation of each of the segments is same irrespective to whether the segment is related to a table or related to an index or related to a partition table, partition of a table, or related to a partition of index. And there are other types of objects also, like bitmap indexes and cluster tables, which can change the behavior up to some extent. But when it comes to physical representation, it is same. Data will be stored as part of the blocks, and contiguous blocks are called as extents, and those group of extents which could be scattered between multiple database files is considered as a segment, and those segments will be associated with a table or an index or a partition or a cluster table, any object that actually stores the data inside it as part of the Oracle database. That being said, we have seen how the data is represented as part of different objects which can hold the data. As part of subsequent videos, we will see how the data will be copied, or how the IO will be performed at the time of writing the data into a table, and also reading the data from a table. And then we will go for the other important topics. That being said, I hope you are enjoying the content on my channel. If you like this video, please click on the like button. If you want to provide feedback or ask any technical questions, please use the comment section of the video. And if you are not subscribed to my channel yet, please do so. You will get to see a lot of content like this over time. Thank you. Bye.